Hi everyone. In this video I want to go over the first reaction in ethers and epoxides. And here we are going to make a ether, specifically a symmetrical ether, using primary alcohols. What we need are primary alcohols, plus H2SO4, strong acid. Typically there's going to be heat, and we make a symmetrical ether. One example is using methanol, and what is going to happen is two methanol molecules are going to come together to make an ether. Sometimes the professor will put the number 2, the coefficient 2, to show that they're two combining. We could draw it like this, and we should have heat. Oh, now this is a methyl alcohol, so it's even less crowded than primary alcohol. If you want to be super specific, then you can say methanol or primary alcohol. Let me do an example with a primary alcohol. Okay, it's definitely primary, and let's see what's happening. We just have an oxygen with two of those alkyl groups on each side. Let me put a dot here just to make sure that I have the right number of carbons in the product. And I have this. There's your dot. There's an oxygen. There's a dot. And there's the other side of the ether. Okay. Alright, let me go through the mechanism. And some of you may have caught that this looks very similar, identical actually, to a reaction that you've done in the past, and I will explain how to choose whether to do this reaction where you make the ether or the other reaction. I might as well just tell you now actually. We're going to recall alcohol dehydration. This is, we'll call this primary, alcohol dehydration. That's the same thing as elimination actually. We're removing an H and an OH. And since it's primary, it's going to be an E2 elimination. Because if I have this alcohol here, and I react it with a strong acid, you had learned that you can make this a good leaving group and you get rid of the beta hydrogen to do an elimination. So there's a dilemma, right? The dilemma is, for these two reactions, we have the same starting material. Okay, are we supposed to do this substitution to make a symmetrical ether, or are we supposed to do an elimination? Before I explain what I'm going to do on the exam, or how I would test this, this is technically, and we'll go through the mechanism, this is technically an SN2 reaction. We're substituting the OH with this alkoxy group. But don't worry about that right now. I will make it very clear. Typically, if you use very hot conditions, you will lean towards the ether formation. Okay, but for now we are going to focus on the formation of an ether, symmetrical ether, via an SN2 reaction. Now we can do the mechanism. Okay, we got to start with protonating the hydroxyl group. I know I'm going to kick out water via an SN2 reaction, so I am going to draw this bond. Positive, plus, okay, what's next? Well, keep an eye on what product we need to make. It's very uncrowded. It's very easy to attack. Now don't forget that hydrogen here is still attached. But also this oxygen made a bond to this carbon. We kick out a leaving group, water. This is positive. And we get, okay, that is grabbing the proton, and we're making this bond a lone pair. I'm going to draw the shorthand line structure, and we created H3O+. Okay. Now, that's the full mechanism. The rate determining step is again where the leaving group leaves, RDS, and because it required 2 molecules, this is a SN2 reaction. Okay. We substituted literally the water with this methoxy group. Eventually becomes methoxy when you remove the hydrogen. Now, can you do the same type of mechanism with this alcohol here to make the symmetrical ether? Okay. Let me write that down. Oh. Maybe you could test yourself. So the problem is draw the mechanism for this reaction. Now typically when you have sulfuric acid, typically you would be allowed to use H3O+ to do the protonation down here. Okay. Eventually you will have H3O+, but also sulfuric acid is sold with some water, even if it's super concentrated. Again, you could put H3O+ for the protonation. Okay, maybe that makes things a little bit simpler. Alright, why don't you pause the video and draw the mechanism for this reaction to get practice, and when you're done, unpause the video and make your corrections in a different colored pen when you see how I answer this problem. Okay, the alcohol looks like this, primary again. I'll explain why primary it's important. Let me use hydronium to do the protonation in this case. The oxonium ion is primary. So you're not going to make a primary carbocation, that's very unstable. You're going to attack right away. we did make water. Okay. And we are going to attack this oxonium ion with another alcohol. I mean the same alcohol, another molecule of the same alcohol. Pretty simple. And we get this. Let's see. Let's put the H here. Make sure you have the right number of carbons. Positive. Grab this hydrogen. Okay, that's the full mechanism. Sometimes your professor will ask where the rate determined step is. It's that one. It is an SN2. Alright, very simple, right? Just have two primary alcohols and add acid. We make the symmetrical ether. Now, what's the danger if you have a secondary alcohol? Let me describe that here. Let's say we have two propanol. Oops, like this. And let's say we're trying to make an ether. What's going to happen here is that since this is secondary, the attack on that oxonium ion, so I'm not going to draw out the full mechanism, but we have this. Because it's secondary, what's more likely is you're going to form the carbocation, the secondary carbocation, which is pretty stable. And at this point, let's see, we have water. We are not going to do a substitution. You are going to do an elimination. And remember how elimination occurs? Remove the beta hydrogen. This would be your major product. Okay. But you can remember that because, again, for this reaction to make a symmetrical ether, it has to be a methanol or primary alcohol. It fails when you start to make an ether out of a secondary alcohol. Alright, now let me give you some practice. Let's see. This is going to be fill in the product, and again, I will make it clear whether I want you to do a substitution or elimination. For instance, that's a primary alcohol. We'll call this number 1. You have H2SO4. I'll use heat, and maybe in parentheses I'll say here do substitution. Okay, what do I mean by substitution? Again, you're doing the reaction where you make the symmetrical ether, because the substitution is what? You substitute this OH with this CH3O. Okay? So we do have a leaving group, and we do have a nucleophile. That's the substitution reaction. Now, if I'm more interested in the elimination product, here's the same primary alcohol. Again, same conditions, but less hot. I know that I teach dehydration with some heat. Again, some professors actually put the temperatures like 180 degrees C versus 140 degrees C. I'm not going to do that. Instead, I'm just going to plainly say what I want, and I'm going to say here, do elimination. Make the alkene. Make the alkene. Now 3, what if we had this? What if it wasn't primary and I add acid? Okay, I wouldn't give a hint. My students should know that you're going to do an E1 reaction. You're going to make an alkene. Okay. Do you want to pause the video and fill in the 3 products? All of these will only have one major product. Pause the video, and then when you come back, make your corrections in a different colored pen. Okay, here we're going to do substitution. We're going to substitute at this carbon at the dot and make the symmetrical ether. Here we'll do elimination. Again, I will tell you, some textbooks want you to make the distinction by what temperature you're running the reaction under, but I don't want to be concerned with that. And we're doing elimination. Just don't forget, here's your, oh no, this is your beta carbon, and you're making a double bond there. That's a E2 reaction. Did I say E2? Yep, E2 reaction. Now over here, right, this is secondary, and you're going to do an E1 reaction. Like that. You go through the carbocation. Here, you actually don't go through the carbocation. So let me list those mechanisms. SN2, E2, primary alcohol, and this is secondary. So this will shift over to E1, make the more stable carbocation, and do the elimination. On the next video, I'll go over another way to make ether because there are limitations. What is the limitation? Well, the limitation is it has to be in symmetrical, right? That is a limitation because what if I want the groups on the oxygen to be different? And I'll end off with that. So here, this is a limitation.